Here. Yeah. So we're going to start by, this is lecture 23, and we're going to be talking about, start a discussion of scattering matrices. We're going to build up towards it. And let me review quickly what we discussed last time. We talked about interactions in path integrals and Feynman diagrams. We started with a generating functional of an interacting theory, for example, scalar field theory. And there's a path integral over the field phi, and then this is the kinetic part, the free part of the interaction. And then this is the free part of the theory, and then this is the interaction part of the theory. That, as you can see, I've only taken to be a function of phi and not pi or derivatives of phi, time derivatives of phi, because otherwise the path integral and the phase space would not, this path integral would not be justified. And then introduce a source. So the classical equations of motion come from a variation of this action that says that the Klein-Gordon operator acting on the field phi plus the derivative v prime of phi, this is like force, right, is equal to a source. Now, this is the classical equation of motion. And then we said that you could view this, bring J on the left-hand side. This is, as an operator, you could view this acting on the generating functional, giving you 0. Now, this is the equation of motion operator in the presence of source. And this is the so-called Schrödinger-Dyson equation that we said gives you a formal but a non-perturbative definition, not definition, but formal, well, definition in a sense, of quantum field theory. Basically, what you would like to do is you would like to take derivatives with respect to ij, and then set j equals 0. And this, if you do that to this equation, what you will find is an infinite set of equations that relate the correlate their different point correlation functions. If there are any questions at each point, please ask. Then we talked about perturbation theory, and we took as an example the lambda phi 4 term. We often put this, take out this 4 factorial term just to simplify our combinatorics. So we saw that when we had Feynman diagrams, combinatorics will come into play, which is the symmetries of the diagrams, and it's convenient to remove this 5 factorial in the definition in the action term. All right, so the Feynman rules in real space would be a propagator for scalar field xy. This is a propagator I delta of f. This is a Feynman propagator, right? Which is the Fourier transform of the p squared minus m squared plus I epsilon. Then we said every time you have a interaction vertex x, you have minus I lambda. And then if there's a cross, that's a source insertion, that's ijx. And then the symmetry to take into account, when you write down Feynman diagrams, you have to divide by symmetry factors of the diagram. And of course, all the loops correspond to integrals, right? Similar thing in the momentum space, we had these integral loops over momenta that are not external legs. The symmetry factors, the vertices come with minus I lambda, the interaction term. And then there's a conservation law of conservation of momentum and energy that corresponds to every vertex as one expects, right? Any questions about the Feynman rules for in the case of scalar field? We also discussed Feynman rules in the presence of for fermions as well, and then I'll come back to that later in this lecture. So we said that if you take the log of the partition function, the generating functional with a minus I, this is an effective action. If you take derivatives of I del j of this gives you the connected correlators. So for example, the 2-point function at order lambda, we saw that this is the free propagator. The first order correction to it is the one loop self energy, right? And then there are higher order terms. This is the only Feynman diagram we could draw. The Feynman diagram represents an integral that we saw as UV divergent. In the Fourier transform, Fourier space, this term corresponds to what it does is that we saw to the order lambda could be repackaged as a quote-unquote renormalization of the regular free propagator. Renormalization here means that it could be rewritten as just a free propagator with a shifted mass, right? And the amount of shift is related to a propagator 0, right? That's a divergent piece, but we will not deal with it for now, right? So, but that's the structure of it to order lambda. Then if you look at the 4-point function at order lambda, there are no corrections, but then there are first order corrections or order lambda squared. There are 2 vertices and there are one loop. There's this term, there's this term, and then there are these terms. These are combinatorics. There are 3 different possibilities. Are there any questions? All right. So that's a summary of what we went through last time. I'm going to pause a little bit longer. Are there any questions? Okay. Today, we're going to work towards scattering matrices. And as a warm-up, we're going to one of the main things that we're going to be trying to, one of the main tools that we're going to be using in the next couple of lectures is to go from correlation functions towards the scattering matrix. So the correlation function, you know how to calculate it, at least very formally. It's found by taking derivatives of the generating functional. And we would like to go from that towards the S matrix. As a warm-up towards doing that, we're going to derive something that's called the spectral representation. So this is one of the very few things that you could say about an interacting theory. That's very exact. So let's consider an interacting scalar field. All right. So here I'm writing phi dagger, which means that I'm considering a complex scalar field. I can drop the dagger and talk about the real scalar field. It won't really matter. This is a 2-point function. In quantum field theory, as in quantum mechanics or any other quantum system, you could define a resolution of identity, right? You could insert a resolution of identity here. And here, what these are basically all the energy eigenstates of the Hamiltonian. Now, we're going to discuss a little bit what these states are, but they include, because quantum field theory is a multi-particle theory, they include 1 particle states, 2 particle states, multiple particle states, right? And every state that you include, if you boost it, those will also be new states, eigenstates, right? So you have to include, this includes all the boosted stuff as well. Actually, yeah, okay. How do I want to say this? Yeah, no, I'm gonna take this. Yeah, that's right. That's correct. So let's say that let's consider a 0 momentum eigenstate of the Hamiltonian, right? This is basically the eigenvalue of such a state, we're going to call m lambda. Then we could boost it to momentum p, and then we saw in representation theory Lorentz group that those states will be naturally appearing in our representation. So there's a resolution of identity. We'll have an integral over these boosted states. We're going to see that. Okay. Here it is. So what is the resolution of identity? Well, the simple state is the vacuum. Then you take all the 0 momentum eigen vectors of the Hamiltonian and you boost them. Well, they have some mass, whatever the mass is, and you boost them. What this is this is the, if you recall, this is just the integral over the d+1 dimensional momentum with the condition that there's a Dirac delta function that imposes the on-shell condition, the fact that this state has energy m lambda. So if you write it in the, if you perform the P naught integral, you end up with this form, right? And omega p's are, of course, p squared plus m lambda squared. But as is, these lambda p's need not be single particle states. These are just some zero momentum eigenstates of the Hamiltonian. They include multi-particle states as well, that they have total energy m lambda. Good? Is that clear? All right. So, all right, so here it is. This is our two-point function. This is for an interacting theory. Let's insert the resolution of identity in the middle. This is sum over lambda. These are the boosted expressions that you put in the middle. Okay? So now the first thing you notice is that this is inserted at x and this is inserted at y. You could use the translation operator to, so this phi of x could be thought of as e to the power of I p mu x mu. Phi is 0, e to minus I p x mu, p mu x mu, right? And so you could bring it to 0, but then you, at the cost of introducing these operators, e to the power of minus I p mu x mu, and on the left and right. Well, one of them will act on the vacuum. Vacuum is invariant, so that does nothing. The other one will act on this state with momentum p. So this from the from going from the e to the power of minus I p mu x mu that you find from this guy on x on the left, you pick up this term. Similarly, you do the same for this term. There will be an e to the power of minus I p sitting on this side that acts on the vacuum, that gives you nothing because the vacuum is translation invariant. The other term will give you e to I p y, p mu y mu, right? And then you end up with this expression, right? And of course, this p has to be on shell because these state lambda p are on shell, right? These have a fixed, and the relation between momentum and energy is basically omega of p mu, right? This is the relation between their mass and momentum, right? Is that clear? Then you could further use boost uh, invariant. So this is what it is this is lambda of 0, the boost operator. And then you could bring the boost operator to this side because this is this operator will not evolve under boost. You could bring it on this side and it will be killed by omega. So you end up with this beautiful simple expression for the two-point function. Next, what we're gonna do is we're gonna notice that this structure that we see resembles actually this is precisely what the two-point function is. If you recall, this is what the two-point function is. The point is that this expression seems to not depend on the kinematics of these terms. So you could write down this term as just integral of d plus 1. This capital D is d plus 1, right? Space time as and the I over p squared minus m lambda squared plus I epsilon, and these are the space-time forms, right? Well, we just write it in this form. Everything we've said is about an interacting theory. Everything is just fully general. Now, you notice that if you have a free theory, okay, no, actually, what another thing to say is that now bring the sum lambda inside. So what this looks like is that we learned that the propagator of an interacting theory could be written as a sum over lambda of the propagator of free theory with some m lambda squareds, and these are the coefficients, right? So what I'm saying is that this is the propagator that this is the propagator of the free theory for some values of masses. These are the zero momentum energy eigenkets of the Hamiltonian, right? M lambda. And then there are these coefficients that sit next to it. So if you define the so-called spectral function as some function, this is a density associated, well, this is just a density that could be defined this way. And using this definition, you repackage your interacting two-point function as an integral over mu squared 0 to infinity of I rho mu squared, p squared minus mu squared plus I epsilon. This is called the Callan-Lehman representation. All right. Is everybody who's with me? I'm going to give you an interpretation of this in a second, but are there any questions so far? Okay, so what is this Callan-Lehman representation? It tells you that so what is this expression? Let's just try to get some intuition from the right-hand side. If this were free theory, what would a free theory with mass m squared, what would be the spectral density? What would the spectral function be? The spectral function will be Dirac delta function of mu squared minus m squared, right? Then if I plug in here Dirac delta function mu squared minus m squared, this will become I over p squared minus m squared plus I epsilon, which is the free theory two-point function propagator. So what we learn is that the interacting theory behaves like the interacting propagator behaves like is an integral over a whole set of propagators with different masses. And then there's a density that tells you about how much of each mass there is contributing to the full interacting propagator. Is that good? Are there any questions? All right. So this is called the Callan-Lehman representation. You just write down the two-point function interacting two-point function propagator in terms of the free propagator, but it comes at the cost of getting a density. And then, yeah, basically that's what it is. So the spectral function rho of q squared encodes the spectrum of the theory, right? Because basically, if this rho of q squared, if this is a bunch of Dirac delta functions, what it tells you is that it tells you about all different energy eigenstates of the Hamiltonian. We'll see in a second that it's more complicated. You could actually easily already see that it's not a bunch of Dirac delta functions. And the propagator is the residue, and the residue of the, yeah, so sorry, the spectral function is the residue of the pole at p squared equal mu squared, right? So it gives you the number of states at a given mu squared. Right? I just said that if the theory is free, you just have this. We're going to see that when you have perturbative interactions, we just saw that actually, as a matter of fact, the two-point function, at least at one loop, what happened was that when we looked at the two-point function, the mass was shifted. So it looked like that the Dirac delta, the spectral density will become will be still a spectral density with some shifted mass. And then there's a parameter z that sits in front. This I have not explained yet. We're going to see that. So this is generically the structure of it, right? And then there could be multiple particle states, right? The story is a lot more complicated. So the single particle, when you include interactions, the mass of a single particle is shifted, but there's still a pole. The moment you get to the two particles, now what you could do is now there's a continuum of states. There's a continuum which corresponds to a branch cut for the function, the complex function on the q squared plane. right? So, and this, if this were a free theory, this would be just 2m squared, right? This is the threshold, the beginning of the this branch cut is the threshold for pair production. This is when you have enough energy to create a pair of particles. And then there's a continuum of there's a continuum beyond this point. Does anyone have an intuition of why there's a continuum here? It is think about why you get a continuum here and how you could deduce there's a branch cut over there. All right, any questions? That's a very good. This is the spectral density is a very important concept in physics, and you should familiarize yourself with it. Do not take this lightly. Do calculate and see. Try to interpret this. Are there any questions? All right. So our goal is today is to start building towards the S matrices, scattering matrices. So a little bit of reminder, I don't recall if we had this discussion before or not. Maybe I briefly went through this. So scattering matrices or S matrices are some basic observables in quantum mechanics. To define them, we make an assumption along these lines that at initial time ti going to minus infinity and final time tf going to infinity, the interaction turns off adiabatically. This is sort of an assumption we're making, okay? Then if that is true, it means that at early time, minus infinity in time, the theory is free. So the solutions are basically a bunch of incoming particles, free particle waves. And at plus infinity in time, the solution is also a set of free particles. And the S matrix is the overlap of the incoming and outgoing particles, right? So the plane waves are solutions of the free Schrodinger equation. These are the in states. There's a Hilbert space at minus infinity in time. Oh, sorry, this should be, yeah, okay. These should be in. And then the plane waves of the solutions of the free Schrodinger equation, these are the out states as t goes to infinity. So the S matrix is basically you start with some initial psi n, you evolve it by e2 minus IH TF minus TI, psi out. And you send TF to infinity, minus infinity, you're evolving from long time going until late time in the future. And of course, you always have to do this adiabatically turning off the Hamiltonian, or as we saw, one way to make sense of it is by shifting this t, giving this t a small imaginary I epsilon, so that the path integral converges and the Fourier transform is just fine. Good. So this is what the S matrix is. So it's helpful to go through the S matrix in single particle S matrix and a quantum mechanics. When what you're doing is a lot simpler. You just have a potential and you're scattering off of a potential. In the first order in Born approximation, we discussed this, that your psi of n, which is some superposition of the n particles, right, propagates, this is a propagator, right, to some state at time tf at positions qf, right? This is the free propagator, but the interacting propagator at the first order, what's going to happen, what's going to have is that it's going to have this guy propagator insertion of v at time t, another propagator, right? So these are these diagrams, if you recall, we drew them like this. Oh, I don't know how to draw this. We drew them like this, right? Um, that's this term, right? Then the S matrix is basically the overlap of this evolved state at late time, the state evolved at late until late time with some psi of out, right? And then we saw to the lowest order this initial final S matrix. What it is just momentum conservation. In a free theory, at the 0th order in the coupling, all you expect is momentum conservation. The next order term that has to do with this diagram looks like minus IH bar, or minus I over H bar, the integral of these. There are two insertions of the a propagator, right? There's a insertion of the interaction in the middle, and then you're integrating over the initial and the final wave packet. Feynman diagrams, as we saw, are a helpful way to organize things. Now, are there any questions here? Any thoughts, any questions? I'm going pretty fast, actually. All right. Now let's talk about the S matrix and what we're going to call LSC reduction. So we're not going to do justice to this. I'm going to high level motivate what LSC reduction is first in terms, in words, and we're going to come back to this several times and discuss it. But let me first explain what the LSC reduction is. The idea is that so far we've been talking a lot about the correlation functions of quantum field theory. And for example, we talked about G2, G4. These are the 2-point function, 4-point function. We talked about them in the real space. We talked about them in momentum space, right? So we also introduce S matrix. The question that comes up is how are the correlation functions and the S matrix related, right? So we would like to do that. We would like to relate the S matrix with correlation functions. So for example, imagine you have a S matrix where there are two in particles coming in, they scatter, and then there's two out particles going out, right? So there's that process has four variables, right? There is incoming momenta. This is scattering problem, P1 and P2, and then outgoing momenta, P1 prime or P2 prime, right? You do expect that the S matrix to 0th order will have to, well, you expect a conservation of momentum here, right? That's what you expect. So Dirac delta function is basically what the structure of the S matrix is in the absence of interactions. But the question is, how is this related to, how is it related to the 4-point function? Because if you consider the 4-point function, Fourier transform it in the Fourier space, 4-point function is also a function of 4 momenta. And the question is, how are these related? So the first guess you might have is that because the S matrix, in the S matrix, the 4 momenta that go into the S matrix, in the 2-to-2 scattering, these are momenta that characterize the in and out states. The in and out states are states of free theory. So these momenta are on shell. So it would be natural to guess that we could relate the S matrix for the 2-to-2 scattering, for example, to some on-shell limit, something going on shell inside the 4-point correlation functions. More general, and then this is what the LSC does for you. So it basically takes the 4-point function Fourier transform momentum space and then takes something on shell. You'll see there will be a residue, there will be a pole, there will be a residue, and then you extract the residue and it will be the S matrix, right? So that's the basic idea. More generally, if you have a N to M scattering, that would be related because these are in and out states. Again, N in states and out M out states. All of these N plus M momenta are on shell, right? So that would be related to acting on the N plus M point correlation function in momentum space, by some operation that takes things on shell. So I'm just going to quickly, as we go today, later on, I'm going to tell you what that relation is. We're not going to derive it. We're going to come back to this and justify it gradually further. Are there any questions about what the LSC reduction is? So it relates the n plus m point functions, correlation functions, to n to m scattering matrices. Are there any questions? So the S matrix, SB alpha, is the overlap of the in alpha state and B beta out states. And we said that if there are no long-range forces, or if we adiabatically equivalently, we can say these are not proper physical justifications. These are just set of words we sometimes say, but the story is a little bit mathematically rich, and we're trying to avoid the full discussion of this. I recommend reading Weinberg about this the very definition of the scattering matrices. So yeah, we said that what we do is we adiabatically turn off the interaction, so that the in and out states, asymptotic states, are free particle states. So as we said, again, I'm repeating this. What the idea is that the LSC reduction formula gives the S matrix in terms of the amputated correlation functions. All right. So what was the S matrix? The S matrix is some alpha in overlap with some beta out. Now, so that's what it is, right? So you could write this as alpha in, beta in, some S here. Right. Very good. And this S, because it has to do with the unitary evolution of the Hilbert space of n to the Hilbert space of out, well, this has to be unitary, so which means that S dagger has to be identity, right? And good. Are there any questions? So here's what the LSC master formula is. I'm gonna give it to you first without justification, just telling you what the structure of it is, but gradually we're gonna go ahead and justify it, okay? And of course, because the presentation of the whole Feynman diagram or perturbation expansion we discussed was in terms of this guy, in terms of the generating functional, you know how to take derivatives of the generating functional to get correlators, all right? So that's what correlation functions are. You would like to know how to extract the S matrix from the generating functional. The idea is the following: apply this operator, this crazy differential operator. What is it? It's an exponential. There's time ordering here. You have to be careful, right? Sorry, this is a normal order. It's an exponential of I integral of d of y phi of in. These are some in fields, right? ky is the free field and free. This is the free say Klein-Gordon equation, right? Let's say you have a theory which is like scalar field with the free part of it is just Klein-Gordon equation, and then there are correction terms to it which are interaction related. So this is the Klein-Gordon operator, right? And then this is del I. The derivatives with respect to J. So when you take these derivatives, you bring down fields from in the expression for Z of J inside the path integral. These are the Klein-Gordon operators acting on it, right? This is a very structure, just very high level. If I want to say, given the generating functional, you know how to calculate the correlators, and this is the expression for the S matrix. Are there any questions about the expression for S matrix? I've not justified it. We're going to discuss this more.
So is this like an operator, or is this the matrix element itself?
No, this is the operator.
Okay.
This is the operator. Yes.
So you would get the element itself by acting this on the end state or whatever.
Correct. You have to take matrix elements of this.
Okay.
Right. Right. So you see, this is an operator, right? This is an operator. So as you expect, that's why I put the hat here. Any other questions? But I think at the moment, this presentation is way too formal. I don't expect you guys to see exactly what this does, right? But we're gonna do the calculations and gradually see. But the insights to start with, I told you in advance. What it is that you take the S matrix that has n particles, incoming momenta going to m outgoing momenta. That's going to be related to an n plus m point correlation function in Fourier space. And the fact that these momenta, the S matrix momenta are on shell is going to show itself as some sort of poles. Well, there will be poles in the expression as momenta of the correlation functions go on shell, and the residues of them are going to be related to S matrices. Good. All right. Like for example, yeah, maybe yeah, okay. Is that clear? Let's just do the example of the 2-point function in your head, right? The 2-point function, when you calculate the 2-point function, if you pick a bunch of momenta, right? When the momenta go on shell, what you end up with is, well, when the momenta are not on shell, you have 1 over p squared plus minus m squared plus I epsilon, right? When they go on shell, you pick up a pole, right? That's when p squared minus m squared is 0. But yeah. Good. All right. Yeah, this is what yeah, this is what we well, I said these words, and at this point I think it's a little bit formal. We're gonna come back to this and discuss it. But basically this is going to be this operator that acts on the generating function and will give you the S matrix. But just what you need to know is to recall that if given z of j, the generating function, we can also calculate the correlators similar derivative as well. All right. We said this, I think, I believe that maybe, let me just say it again, that S matrix has a piece to it, which is identity. That's when there is no scattering. This is basically the boring piece when the theory is free. This piece to the S matrix is just basically tells you free particles, incoming particles, propagate all the way to outgoing particles. And what this piece is just the conservation of momenta, right? So for example, this piece clearly will vanish for any scattering process that goes from n particles to more or less than n particles, right? If the theory is free, then there's no particle creation. These guys just propagate freely, and there won't be a term here, right? This is just when you have the when I write identity, that means that these are the diagonal elements, right? Good. So we often define this matrix T hat. Instead of working with S, we work with this matrix T hat. And it's just the point of it is to remove the identity piece of it, right? And then we put an I here. Do you guys know why we put an I there? So that this matrix T is self-adjoint, right? S is supposed to be unitary. So if this was an expansion of well, it's not necessarily self-adjoint, but if this was an expansion to the first order, it would be a self-adjoint operator. Good. All right. So what does the structure, what does it look like structurally? What comes out when you will look at the matrix elements of T, right? It's just, instead of talking about matrix elements of S, we're talking about matrix elements of T. So the matrix elements of T capture the contribution of the interactions, the actual scattering, right? Because if there's no interactions, this S matrix contains a piece, but you would not call that scattering, right? Because particles just go through each other. So if you look at the matrix elements of T operator, you always, we saw this example in doing the first Feynman diagrams that we worked out. There always will be some sort of a conservation of momenta, right? I think that's an important law of physics. So it's convenient to just take this factor out of it and then define IM of K to P. This is called the invariant matrix element, right? So it's pretty clear that if I have instead of talking about the S matrix, I can talk about the T matrix. And instead of talking about the T matrix, I can talk about the invariant matrix element, right? This I curly M of K incoming momenta going to P outgoing momenta. This is super compact notation. This K means that there's a series of K1 to Kn going to P1 to Pm if you're describing an N to M scattering, right? These are all the initial and these are all the final momenta. Good. So that's what I'm just setting the terminology, right? So this is the S matrix, this is the T, this is the invariant matrix elements. We often calculate these guys, right? And then in scattering, there's something else that's called the cross section. That's what we actually observe in an actual scattering problem. The point that you need to know for now, we're going to describe this in more detail, is that what we observe is something called cross section. So what is cross section? Cross section is the norm of M. So this is a complex function, right? Is M squared times a bunch of factors that are decided by kinematics, right? There is some sort of a geometric configuration and the scattering, the incoming angles and outgoing angles, right? And all of that is decided here in the kinematics, right? But the crucial part of it, that is where the core of the calculations, we're going to describe this kinematics later, but the core of the calculation is going to be this M squared, right? This piece. Good. Any questions? So this is just to set the terminology. When we talk about S matrix, there's a T part, and that's what we care about. And then there's the T part has the invariant matrix element. The invariant matrix element squared is what up to a bunch of kinematics that we're going to describe. It's not going to be profound, but you have to learn it and make it intuitive for yourself. What we observe at the end of the day is our cross sections. That's what we observe. Good. Any questions? All right. So, remember that this conservation of momentum is always necessary. When we write down your Feynman diagrams, every place where there was a vertex with a bunch of modes meeting, momenta had to be conserved, right? Like every vertex in Feynman diagrams come with momentum conservation. So this is going to be invariably there no matter what. All right. In perturbation theory, what we have is that this S is e to minus I integral of V in interaction, right? So if the interaction term is 0, this is just the identity piece of the S matrix. By the way, is it clear that I'm using the interaction picture? Is that familiar? That we in quantum mechanics we often, not often, almost always, we formulate a scattering problem in the interaction picture. Hence, this as the evolution operator. But these are okay. I assume you guys can make sense of that. If you don't, you either know it or if you don't know it, you can make sense of that. But do pay attention to the fact that we're using the interaction picture. All right. So a little bit of notation and description. We're going to be doing a lot of Feynman diagrams, so this is going to be helpful. Imagine you have a propagator, we're going to talk about the incoming and outgoing states, right? These are the part of the Feynman diagrams these are the external legs of the Feynman diagram, right? So if you have an incoming particle, it's a wave function. This incoming particle is, these are the solutions that, because this is the particle that comes from, this is the initial wave function from minus infinity in time, and this is a free theory, right? Back then it's a free theory, so the solution, the Klein-Gordon equation, is just e to minus IPX, right? These are the waves that propagate, and in Feynman diagrams we show them like this. We draw them like this. The outgoing particles is just not very clear what I'm drawing them like this, but it's pretty, you should understand that there's in Feynman diagram, there are always a bunch of incoming and outgoing particles, right? There might be some symmetries in the diagram, but so the outgoing particles are going to be e to the power of I px. The sign flips, right? It's just the fact that these are the complex conjugates of those, right? So the in and yeah. Now, if you have a fermion, right? Dirac fermion, these are four-dimensional vectors, right? So there's a, so you could think of them as what it looks like is that there is a fermion propagator, e to minus IPX, u of p. Remember that these are the things that we solve for in the in Dirac equation, mass in the free Dirac equation. These are solutions to those guys, right? And there are two of them, right? There's just like there's a spin here, right? There's a up and down spin. So there are two of these guys, but hopefully you recall these are vectors, right? And the fact that this is a fermion, I'm going to draw by the putting an arrow here to just say that is the direction of the flow of charge. If I had in my scalar field a complex scalar field, then what I would have had is I would have had to put in. Do you guys see my cursor? No?
Yeah.
Okay, good. Yeah. I would have had to put an arrow here because that's the direction of flow of charge. Then phi dagger would be the similar incoming phi dagger would be the same thing, but with the opposite arrow, right? And because the in because yeah, but the very good. So here hopefully it's clear. So the fermion, the incoming fermion is like this. The incoming anti-fermion is gonna have the arrow in the opposite direction because this is the direction of the flow of charge, and this is V bar, if you're V bar at P e to minus IPX. The outgoing fermion is going to be U bar of P to pi IPX, and the outgoing anti-fermion is going to be VP e to minus IPX. I'm not drawing the Feynman diagram. The arrows, hopefully that is clear what the arrows look like. Then for photons, it's similar. You have we draw them with wiggly lines, the incoming photons. Oh, I think I messed up. This has a minus sign. And then this guy, the outgoing does not have this guy has plus. Yeah. Yeah, the outgoing should be plus. All right, so these are just wiggly lines. These are the Feynman diagrams. Good. So let's work out as an example. We're going to work out two examples just to get used to the diagrammatics, right? What these guys look like. All right. Consider a 3 plus 1 dimensional theory. The matter content of it is a real scalar field and a Dirac fermion. All right. So there will be a Dirac term, free Dirac term, which was psi bar d slash psi. If there's a mass term, you shift that by mass. And then there's a Klein-Gordon term for phi, right? Phi box plus m squared phi. And then we're introducing an interaction term. G is your coupling, psi bar psi phi, right? This theory has a vertex that couples that we are going to draw like this. Its value is minus IG. This is the term that corresponds to it in the path integral, in the Feynman diagrams, right? And what it describes is a fermion vertex, right? So this is a fermion vertex. well, actually, depending on how you want to interpret this, but okay, yeah. All right, so let's go with this. Uh we're we're gonna draw this diagram, and this is the value. This is the Feynman diagram value for it. So let's consider 2-to-2 scattering. So the incoming momenta are P and K, and the outgoing momenta are P prime and K prime. We're going to consider a fermion-fermion scattering, right? So the fermion-fermion scattering is what we're going to consider. And it should be hopefully clear that the only way to pick up a correction is at order G squared, right? Where you need a pair of these guys inserted. Good. Is that clear? So you're gonna have to insert a pair of these guys. Now you're gonna pick up a propagator in the phi, and then these guys are gonna get contracted with these, and these guys are gonna get contracted with these, right? So any questions? What
The,
this? Yep, go ahead.
the second phi in that expression, is that an operator or is that the field at y?
So this operator is in this point y.
Thank you.
This operator is at point 6, x, right? I've
Yes.
inserted two vertices. One is at point y, the other one at point x. Good.
Okay.
So this is propagated from x to y, and this is propagated. These points, both points are at y. So perhaps I think this a little bit less familiar is that I'm writing this in these terms are in real space, but up, like you could write them in the momentum space, and I'm gonna do that in a second, and you're gonna see that become natural. But what this notation means that this is phi psi bar psi y, because if you remember, well, actually, I had it up here, right? When I insert, where was it? I drew the picture somewhere. No? Oh, did I erase it? Yeah, whatever. So when we had these pictures, right? What we're doing was that this was where the interaction was inserted, and we're integrating over this everywhere in space-time, right? This is that vertex you're putting, and you have to integrate over every space-time, but these three guys are all inserted at that point, and these three guys are inserted at that point. That's where the vertex is.
Okay.
All right, so here is the Feynman diagrams, and I'm drawing Feynman diagrams in the, oops. This really sucks. Sorry about that. So I'm drawing the Feynman diagram as the incoming particles are at the bottom and the outgoing particles are on the top, right? This is the convention I'm using for Feynman diagram. Some people use different conventions, but so the P and the sub K are the incoming fermions, right? It's a fermion scattering. So the incoming particles are both like this, P and K. This is the direction of arrows, signifying the fact that these are both fermions. If I had a fermion and antifermion coming, then this direction had to be the opposite, right? So a fermion comes, and this is an outgoing fermion. This is an outgoing fermion with different momenta. And there is a scalar propagating in between. This is order minus IG squared because I have two vertices. These are vertices that are inserted at X and Y. I'm integrating over them, right? There's a boson propagator from X to Y, right? That is coming from this term. Then what we have is we have psi bar psi at X and psi bar psi at Y, right? You Fourier transform them, you're going to get these guys, e to minus I x k minus k prime, e to minus y p minus p prime, and these are you'll pick up so k, yeah, okay. Well, how to explain this? Well, you just Fourier transform and do the contractions here. That's all you need to do. And this is the first term that you obtain. Notice that this propagator is taken care of. This is USP, US prime, P prime. You have to keep indices. Remember that these guys have spin, right? So you're keeping spin general. Now, when you define your in and out states, you should specify spin as well. If you are agnostic about the spin, as is the case of quantum mechanics, you're not measuring spin. You should sum over all spin configurations, and we're going to do that sometimes, all right? So let's for now just consider the spin indices to be general. So there are two diagrams. One is this, and the other one is this reverse one, the swapped one, right? This is the other diagram that you could draw. Now, what is important, and then hopefully you can see that these are just like term by term following the Feynman diagram notation. I have to put a minus sign here. This minus sign is simply Pauli's exclusion principle. Why? Because if P prime is equal to K prime, right, and S is equal to S prime, the output should be anti-symmetrized, right? So the amplitude should vanish. So, sorry, this is just anti-symmetrization of the output. It's a two fermion state. The state has to be anti-symmetric. And the consequence of that is one of them is the exclusion principle. If P prime and K prime are the same and S equals S prime, the two fermions cannot be in the same state, so the amplitude has to vanish. Therefore, a minus sign here. Good? Is that clear? Okay, so the second term, you see that there is still the propagator. That part is unchanged. The USP and U bar, no, sorry. USP and US prime K are unchanged, but the outgoing particles are swapped the P prime and K prime, right? That's all I've done. All right, you have to sum these two terms. These are the two diagrams that contribute to what? They contribute to that M piece. Well, they contribute to the T term, right? Because this is the expansion of the S matrix, where we have dropped the identity piece of things, right? The identity piece would be just this guy propagates here and this guy propagates up, right? They don't interact at all. But these diagrams capture the T. When we draw the diagrams, that's what we're trying to get. So what we're going to do next is we're going to Fourier transform this boson propagator and perform the integrals on X and Y. So let's see how that works. So what we're getting, if you do that from the Fourier transform, when you Fourier transform and perform the integrals over X and Y, what you're going to find is a bunch of Dirac delta functions. This is just like a couple of lines. It's pretty straightforward. You're going to find a bunch of Dirac delta function that will impose for you precisely this piece that I said it always exists. It's just conservation of the incoming and outgoing momenta, right? And then minus IG squared. So this is the T matrix taking this form. And oh, another thing is that the scalar will be unshelled, right? It just comes from the, well, you should do this Fourier transform. But what is the Fourier transform of this? The Fourier transform of this is just I over the unshelled propagator by I epsilon, right? The Fourier transform of it will be P minus P prime squared minus M squared, right? Because here, the conservation of momentum tells you that this propagator will have momentum P prime minus P, right? And it's an unshelled particle. So it will have this term in it, right? And then similarly here, what you're going to have as your propagator is K prime minus P, right? K prime minus P is the propagator, therefore, or P minus K prime squared is what you're going to think, right? This is a scalar mass. So this is the T matrix. Are there any questions? At this order, right? This is the T matrix as order G squared. All right, so as I said, we often discard this I 2 pi 4 delta 4 term, and we write down M, which was the invariant thing. It just takes this form. You can also see that these parts are just sort of trivially fixed by the external legs, right? They're not capturing the details of the interaction. So sometimes when we talk about the amputed diagrams, this is something that we suppress, right? The amputed diagrams, we do not insert any external factors, but we'll get there. So this is the scattering amplitude is tree level. Tree level means that there are no loops, right? So order G squared is the first interaction term that appears, first order interaction terms, the lowest order interaction term that appears in the so-called Yukawa theory. Yukawa theory has a coupling of this form in the action. Now, another thing that's interesting is that you could have a fermion anti-fermion scattering, right? Now, the only diagrams that in the same theory, within the same theory. So here, when you insert psi bar, phi psi bar, this is your phi. This is you just look at the flow of the charge, right? That's what the flow of charge is. And this is another vertex that you can insert. So you could have a process that a fermion and anti-fermion collide, and what comes out is two scalars. Two scalars are what come out, what are things that come out. Now you have to symmetrize the final states, right? Because the final states are bosons. That's basically should be clear that this case you're just adding them. Now in this case, the propagator in the middle by conservation of momentum is going to be this is P prime minus P. Whoops. I don't know how to fix that. Sorry about that. So this is P prime minus P. Oh, why did I write it this way? P minus K prime. Wait a second. So first of all, this is K prime. So this is K prime minus P. Anyway, I might have some typos here, but you know how to keep track of the diagram now, right? So there will be minus IG squared. That has to do with the fact that there are two vertices. Actually, I think these signs are correct, but anyway, you just have to be careful with the way that you're writing your expressions. Right. Okay. Anyway, so now here your income. Yeah, the incoming is going to be US prime P, right? And then V bar S K, this is this term, right? And then you're gonna have US prime P and wait, what did I? Oh, sorry. This is your first term, and this is your second term. The first term has this propagator, and then the second term has this propagator. Yeah, so the propagator is there's a contraction happening here. But this is what your M is. This is what your M is. I think I got the things totally confused. But yeah, this is your propagator. All right, are there any questions?
The P prime one that
I think the sign is wrong here. That's what it is. I think this should be so let's see USP and K. This part is good. This term is good, right? This is the second term. So US of P, V bar of K of S. This term is good. This is this. And then this term is the one that is off. So US of P, and this should be V bar of S of P prime, of course.
why is it P prime and not K?
Because these are the guys that are going, this is a fermion, right? The fermion has P prime. Oh, sorry. Is that what the typo is? Oh, I'm sorry. That's the typo is in the diagram, not in the. Okay. Sorry. How do I? Oh, okay. The typo is this. The typo is here. Good. Thanks for the correction.
Okay.
Yeah, thank you. All right. So we'll So we said that the object of interest is going to be sigma, which is the square of this, right? So we're going to come back to this later and calculate score this matrix, right? But for now, the things that I'm just going to summarize what we went over. I started by talking about the Cayley-Lemon representation. It is a way of writing down the two-point function of the full interacting theory as an integral over the two-point functions of free theory with all sorts of masses. These masses, quote unquote masses, these are actually the zero momentum energy eigenkets of the interacting Hamiltonian. There is a coefficient, there's a function that tells you about how much of each term there is, and that function is called the spectral density, right? So that function is, this is that function. It's called spectral density, right? And in the free theory, this function is just a Dirac delta function of mu squared minus m squared, right? And in the interacting theory, as we like the propagator of the perturbative, when you consider perturbative interaction to first order, what happens is that the one particle propagator is shifted, right, with some z, and then there could be multi-particle contribution of multi-particle states. There's a branch cut starting in the spectrum of the Hamiltonian, right? There's a branch cut starting from the threshold for pair production of particles. Then we talked about the S matrix, right? The S matrix, the things that you wanted to keep in mind. I briefly mentioned connection between the correlation functions and the S matrix. Is called the LSZ. It's what it is it relates, this is the formal expression for it, but what it is that it says it relates the S matrix to the residues of the correlation functions as you push in momentum space, as you push the momenta on shell, right? There will be poles as you push the momenta on shell, and those the residues are going to be the S matrix. But we're gonna come back to that. Then we said every time you have the S matrix, there is a piece of it which is identity that has to do with the free theory piece. We just remove that. We talk about IT, and that IT always comes with some conservation of momentum that we often also ignore, and then we're just talking about the invariance matrix element. This invariant matrix element is the thing that we're going to score to get cross-section up to a bunch of kinematics. This is the observable of quantum field theory. We define the incoming and outgoing states, how we're going to write them, and Feynman diagrams, right? And if you have fermions, you have to keep track of the direction of the flow of charge, right? So then we give examples from the Yukawa theory with this interaction of two processes. One process was fermion scattering. So there are two fermions coming and two fermions going out. There are two diagrams that contribute to it. The fact that you have to anti-symmetrize the final outgoing state, right, requires that you subtract the two answers. This is just because the fermions are, remember the spin statistics theorem, right? They spin half, and they should have fermionic statistics. Now, right. This is what the M matrix is in this case. And then in the other, you could also, in the same theory, you could, sorry about this typo, you could think about the, oh, this typo is pretty bad. No, that's actually good. The typo is, okay, this is it. This fixes it. You could have a fermion anti-fermion scattering that those are the in states, and the out states are going to be two scalars. There are two diagrams that contribute because the out states are both scalars. You symmetrize the result, so you have to add the two diagrams, right? And then these are the fermion. These are the this is the invariant matrix element that you obtain. All right. Are there any questions?
Nima, is that
Yes.
diagram on the left the same as the one before if you rotate it?
Which
The one
diagram?
on that diagram with the one on the left, that one that you are pointing?
Yes.
Is it the same as the one in the previous page if you rotate it
Very
90?
good. Yes, very, very good. So no, it's not the rotated one. So sorry, wait a second. No, so you can see that the propagator in the middle, the guy in the middle is fermionic here. The guy in the middle here is bosonic. So the external legs here, you have 4 fermions. Here you have 2 fermions and 2 bosons. You might be asking about a different process. The Feynman diagrams also can describe the scattering of, if I rotate this on the side, right? Could be describing the scattering of a fermion from a scalar going to a fermion, a scalar, right? These 2 diagrams, they both contribute. If I turn them, if I just like turn my head to the side, they describe a fermion scalar to a fermion scalar scattering. Oh, is this what you were saying? Fermion, fermion, anti-fermion going to fermion, but this is a fermion, anti-fermion going to fermion, anti-fermion scattering.
Yeah, I see that they're different.
Yes. Any other questions? But the fact that you could rotate these guys, and this is something important about Feynman diagrams, right? But we're not discussing that yet. Yeah. For now, you have a process in mind, which is a bunch of incoming and outgoing, and they're different, right? So you just calculate an S matrix element. These are the rules, and you draw different diagrams. Yeah. Any other questions? That was a really good one. All right. If not, so Thursday we're gonna be in person again. I'll be back in the US, flying back tonight. I'll see you guys on Thursday. Thank you so much. Bye.
Yeah.